you can see, there are two possibilities. Okay, there are two possibilities. Let me tell you what are the two possibilities. Okay, let me move this up a bit. Let me move this down a bit. Okay, there are two possibilities. Right? The first possibility is you take this entire area that I'm going to shade in yellow. Okay, you take this and maybe not shade, maybe I'll just, you take this entire area over here. Okay. The other possibility is you take this area. Okay. Now, which one is correct? The top one or the bottom one? Anyone? What do you think?
Bottom.
Bottom one is correct. Why is that?
It can't cross the centroid, so the
Yeah.
top one breaks that rule.
Well done. Okay. So if you use the top one, we have broken rule number what? We have broken the rule that the first moment of area, or so if we use the top one, right? We have broken rule number 4. Okay, we break rule number 4. Why? The first moment of area cannot cross the what? Centroid. But the analysis is still this. This is still okay. We still obey the rule. Okay, we still obey the rule that the analysis. This is still the analysis direction. Okay, so this is still our analysis direction. Okay, but we have broken rule number 4, and Patrick is correct. Okay, the bottom one is correct. And why is it correct? Because rule number 4 is okay, and now the analysis direction is this way. The analysis direction start from what? So this distance relative to the centroid is also its what? Y max. Okay. So do not focus on the Vy. If you look at the Vy, say, but Eugene is coming from the top, right? That's where it gets really really confusing. Say, Eugene, but Vy is from the top. Why we cannot consider above the centroid? Because one of the rules specify that what? The first moment of area cannot cross the centroid. Okay. So I hope you all appreciate what is going on down here, because this is where things are critical now. Okay. So now, if you any questions so far from anyone, are you okay? Okay, I don't hear any. So now the QZ is this now. Okay, so QZ is equal to, so I like to use the width, the depth, and the Y bar. Okay, so we know that the width, so you have to be careful down here. You have the width, which is twice, so 2, right, left and right. The width is equal, multiplied by the thickness, 0.02. Okay, and then the depth, so this is now my Y. Okay, so this is Y plus by 0.03 divided by 2. Sorry, I missed my depth. So depth is equal to 0.03 multiplied by Y plus by 0.03 divided by 2. Okay. Now, y2 over here is because of the left and right webs. Okay. 0.02 is the thickness, 0.03 is the depth, and that is the y bar. Okay. So for this case, and then I mean for this case, you have to be really, really cautious, okay? Especially when you do this analysis. You have to consider the left web and the right web. Okay. So what does this mean? Okay, what does this mean? So I'm going to arbitrarily sketch a line. Okay. So for example, if this is my centroid? Okay. If this is our centroid, and I'm going to draw a y line, a line that corresponds to a y value. Okay, so this is our y line. Right, along this line is what we have constant shear stress. Okay, so along the blue line is where constant stress will occur on that line at a specific y distance from the centroid. Are we clear? Okay. For now, you don't really see what I mean yet, but later on, when we do the example, you appreciate it better. Okay. So for now, you don't quite see that yet. Okay. So we have applied all the 5 rules. So now we go back to our deriving. Okay, our deviation of our equation. Okay. So where we stopped last, we say that QZ is equal to 0.5 b c squared minus y squared. So I'll write the equation over there. Okay, so you have, and I'll still copy this diagram. So the equation or the formula that we're trying to use is shear xy is equal to Vy over Izz Qz over T. Right. So we have already found, or not found, but we know that this is our defined Vy. Now Vy is from shear force diagram. Okay. Later on we will incorporate that into our example. So we know that Qz is equal to 0.5 B. Okay, it's equal to 0.5 B C squared minus y squared. Okay. So next we are going to find what is our Izz. Okay. So ZZ is the axis of interest. And we know that this is our width. And over here, this is our depth. Okay. So this will be equal to, so Izz is equal to width depth cube over 12. So the width is B, the depth is 2C cube over 12. Okay, so this will be equal to 8 BC cube over 12, and this is equal to 2 BC cube over 3. Okay, so the next thing, so we know what is our, or we define what's our By, we know what's Izz. Our thickness T is equal to B, so we know, and we also have our expression for our QZZ. Okay, so now if we're going to write the expression, the shear XY, as a function of y now, right? Because y is the variable, so you have Vy over Izz, which is 2 Bc cubed over 3, right? Then Qz is equal to half bracket or half multiplied by B C squared minus by Y squared, and then again divide by the thickness, which is B. Okay, so we can get rid of, cancel the B, and I'm going to put note that A, which corresponds to the cross-sectional area, right, which correspond to the cross-sectional area, and which is equal to, so the area for the entire structure is equal to what? 2 BC. 2 BC, because it's 2C multiplied by B. Okay, so I'm going to incorporate the area. Okay, so I'm going to split up the equation at the denominator. So shear xy as a function of y is equal to Vy, and this is still half, right, square bracket, C squared minus Y squared. Okay, I'll close bracket. Then I'm going to split the below up, so I'm going to have it as 2 BC, then multiply by 2 BC C squared over 3. Okay, I just split them up. Okay, it's like doing Laplace transform. You just cooking the equation. Okay, so I'll write better. So this is C squared over 3. Okay, so when I've written up the expression, I can incorporate my area. So it's Vy over A. Then we have the half C squared minus Y squared, close bracket. And then this is divided by C squared over 3. Okay. So from here, we know that this is equal to Vy over A. Bring the 3 to the top. So multiply by 3 over 2. And then you have the term over here, C squared minus Y squared, bracket, over C squared. Then finally, we have Vy over A, right? 3 over 2. You have 1 minus by Y squared over C squared, which is what we are trying to derive. Okay, so if we look at the expression earlier, okay, we were trying to derive this expression over here, where shear xy is equal to 3 over 2 Vy over A bracket 1 minus Y squared over C squared, which is exactly the same as what we have over here. Okay, so we know that the shear xy as a function of y is equal to Vy over A 3 over 2 1 minus by Y squared over C squared. Okay, so this equation over here only will work. Okay, let me get the diagram over here. Only will work, right? Okay, it will only work for structures with constant thickness. Right? And we know over here y is a variable. Okay, a variable measured from the datum, right? It's from the datum. So when y, okay, so let's look at this. Like when y is equal to y max, which is equal to c, right? So if the top term is c squared, right? So the shear xy, right? The shear xy at y max will be equal to Vy over A, right? 3 over 2. Now we have 1 minus by c squared over c squared. This will be equal to what? 0, because it's 1 minus 1. Okay. So if we next put that when y, right, when y is equal to 0, right, what we have is shear xy at point where y is equal to 0. Then we have Vy over A, 3 over 2, right? Because this expression right here is 1 minus by what? 0. So this will be equal to 3 over 2 Vy over A. Okay, so this also corresponds to shear xy max. Okay, that is the maximum value that it could achieve. Okay, but remember, this is only true with constant thickness. So when we are going to sketch, okay, when we sketch the shear stress distribution, all right, I'm going to sketch a shear stress distribution. It will look like this. Okay, so this is our axis. Okay, so this is our shear xy. This is our y, and I'm going to draw sketch lightly where the structure starts and ends on the axis. So this one start from here, go to here, and the next one. Okay, so this is our C. Below is our minus C, right? When we sketch our function, it will look like this. And the maximum value over here is our tau max. Okay. This is our tau max. And this is equal to 3 over 2 Vy over A. And over here, the function, okay, of the curve is shear xy as a function of y. This will be equal to Vy over A 3 over 2 1 minus by y squared over c squared. Okay, that is the function of the curve. Okay, I'm going to stop here. We take a 5 minutes break. We come back at 8:15. Okay, let's take a 5 minutes break.